All right, so I'm making it clear once again, today I am recording your class. So everything that's said, so make sure you're quiet, everything that's said will be projected and recorded today, all right? I will pause it when we leave for lunch, and then I'll continue it when we come back from lunch. Write down, take out your notes if you haven't already. Write down the lesson title. This is Unit 2, Lesson 1. Today we are going to learn about the Bohr model, and we're going to learn about the quantum model. And this is all going to lead us to how are electrons arranged in atoms. That's the idea of what we're going to need to figure out. It will take us 3 class periods to figure out totally how to organize electrons into atoms. So it's not going to be something that in one day you're going to be like, yes, I'm an expert in this. I'm going to be honest with you. Out of all of the units this year, most units start easy and get more difficult as the unit goes on. Like technically the nuclear chemistry lesson was the hardest lesson of that unit in Unit 1. It was the one that had the most stuff in it. Unit 2 is opposite, meaning today's lesson is actually the hardest lesson of the unit. And it will get easier as the unit goes on. So in the past, most students have told me that Unit 2 they find to be easier than Unit 1, actually. But this lesson won't make it seem that way. I apologize for that. And I'm going to explain to you the reason why. Have any of you ever done a puzzle, like a 100-piece puzzle or a 500-piece puzzle or even a 1,000-piece puzzle? What's the first step of doing a puzzle, solving a puzzle? You do your outsides, okay. Well, you first have to like open it, right? And when you open it, you see that there's a bunch of pieces and you lay them out. And then you organize them and you put them in an order that makes sense. So here's what's going to happen today. You have to get the puzzle pieces before you can piece them together. And so this is why I said it's going to take 3 class periods altogether to piece everything together. But today, I'm going to be throwing out a bunch of puzzle pieces. And so there's going to be a bunch of pieces of an idea that you're going to need to pay attention to, you're going to need to write notes on. Today, some of it may seem very abstract and confusing, and I'll do my best to demystify it as much as possible. But I'm going to be honest with you, this is one of the most abstract lessons of the year. And it touches into physics. This touches more into physics a lot of times in chemistry. However, as we are looking at chemical reactions, we have to understand where electrons are at in order to know how they move between atoms. And so because we have to figure that out, that's why we have to delve into this topic. So we will be touching some ideas in physics, but there won't be any math beyond counting. You will have to count, like, 1, 2, 3, 4. You may have to multiply by 2. But beyond that, and like one tiny little simple formula, but beyond that, there will be much less math in this unit than there was in Unit 1, just so you're aware. All right, so we're going to go ahead and get started. Unit 2, Lesson 1, Electrons and Atoms. I'm going to define a few things before we go to lunch. When we come back from lunch, we'll get to the real meat of what we're going to learn. So go ahead and write down this first question. What did Bohr propose in his model of the atom? You learned a little bit about this in the video, and we'll go back more over what was proposed in the model of the atom. You can see on the side, the diagram I chose is one of the Bohr models. To kind of give you an idea. What did he propose in his model of the atom? Go ahead. So the electrons orbit around the nucleus as the planets orbit around the sun. So you could liken it to that. That was his proposal. It's actually not the best proposal. There's a lot that's wrong with it, but we still use it. And that was one of the questions I asked you to write. We still use it. You've seen it written in other classes. I'm going to use it as well because it actually gives us the best visual idea of what's going on, even though it's not the most accurate model. So we're going to go over the more accurate model. What are the key differences and similarities between the two? And then why we still use the Bohr model in order to visualize what's going on. All right, so what did he propose? This is the answer. Go ahead and write it down. I also suggest you write the example of a Bohr model. So you have it to look back at. So everything here is important. The Bohr model. He proposed that electrons are found in specific circular orbits, that they move in a circular manner around the nucleus in orbits. And that each orbit, based on its distance from the nucleus, we would call an energy level. So in each orbit, the electrons would have fixed energies, and so we would call those different orbits energy levels. So I'm going to give you some time to write this down. Write down everything that's in those blocks, and then you also should have the Bohr diagram written, so you have it to reflect back to as we are comparing the two models and eventually filling electrons. Yes. You're ahead of me. I'm gonna talk about that. I'm giving you some time, then I have two things I need to say before we move on. One of them Axel's already brought up. Why that letter N? It's not neutron, unfortunately. Okay. Giving about 30 more seconds before I start bringing up those two ideas. I try to have you, if you can, try to write down most everything so you can focus and pay attention to what I'm saying, but only a certain concept. So very shortly, I'm going to bring up two major ideas. Then we're going to cover just a couple more definitions if we have the time. And then we'll go to lunch and we'll keep going when we come back. Here we go. First, so electrons, are they negative or positive? Negative. The nucleus is positive, right? So one of the things I told you in Unit 1 that we have to keep going back to is the idea of charges and how they work, what repels and what attracts. And so knowing that electrons are negative and the nucleus is positive, would electrons be attracted to the nucleus or repelled by the nucleus? So we know that electrons are going to be attracted to the nucleus because the nucleus has the protons and therefore it is positive, yes? So then would it make more sense for electrons to be as close to the nucleus as possible or as far away from the nucleus as possible? So when we're filling electrons around an atom, we're going to want to place them as close to the nucleus as possible. So far, so good? My second question is, well, could I just put an infinite amount of electrons in the first energy level, in the first orbit? And why or why not? Why not? Because electrons repel each other. So it turns out that in every amount of space that you have, you can only fit a certain amount of electrons. And this is because of the idea, well, although electrons are attracted to the nucleus, we know that electrons actually repel each other. Electrons repel each other. Therefore, you can only fit any certain area. This actually brings another idea up as well. As we get farther from the nucleus and the area increases, like the space increases, each orbit's going to be able to hold more electrons because they're farther apart from each other. And so that brings up another key idea that the Bohr model helps us understand, which is one of the reasons we still use it, because it is the best visual depiction of what's going on, even though it's not the most accurate. And we'll talk about, like I said, the key difference is probably when we get back from lunch. The other thing I need to bring up, so that was number one, was talking about electrons and reflecting on, we have to understand how charges work. And that's going to be a continuing theme throughout this class. The second, I apologize for this on behalf of my people being chemists. We use the same letters over and over again to mean different things, so I apologize for this. In Unit 1, when you saw the letter N, you thought of neutrons. But in quantum mechanics, which is what this study is actually of, quantum mechanics is physicists came up with these models. They came up with something called quantum numbers. And N is a quantum number. And it is the result of very complex equations. The long story short, in Unit 2, whenever you see the letter N, it's not talking about neutrons because we're not even going to talk about neutrons the rest of the school year. Like, we're pretty much like, neutrons? They exist. Like, that's the rest of the, we did as much as we're going to do with neutrons in Unit 1. Like, we're never looking at neutrons again. We're barely looking at protons. We're literally only going to be looking at electrons. Why? Because electrons moving between atoms is the whole idea of chemistry. Those transfers are transfers of electrons. So we're literally only going to be looking at electrons pretty much for the rest of the year. So when you see the letter N in Unit 2, N is always going to mean, unfortunately, but you just have to memorize it, energy level. And so for the Bohr model, that means what orbit the electron is in, how close to the nucleus it is, and how much energy it has as a result. And so the final thing to bring up is that electrons that are closest to the nucleus have the least energy, and electrons that are farther away from the nucleus would have more energy. So that's the last thing to bring up. So when you actually see energy level 1, 2, 3, energy level 1 is the lowest energy electrons. Energy level 3 would be higher energy electrons. We're going to stop here for now. We're going to look at the electron cloud model when we come back from lunch, and then we'll continue on the ideas. Make sure you are paying careful attention throughout today's lesson. Like I said, it is the most complicated of the entire unit, but the ideas are very important. Yes. What do you need? So everything else is good. Everything else is good. I'll check it later. All right, remember when you're getting ready to exit for lunch, you're waiting by the back door and you come back through the front door. Phones back out if you had them in during lunch. All right, we are about to get back started, so please make sure you're taking out your headphones and you are going back to your notes. If you need to log back into Google Meet, please make sure to do so. We're going to go ahead and continue. So where we were at is we only discussed the Bohr model, and that the Bohr model has electrons in what's called these energy levels, and the energy levels are the orbit around the nucleus. So the lower the energy level, the closer the electron resides to the nucleus. The farther the energy level away, the higher the number, the farther away the electron is from the nucleus in an orbit. And so that's where we had gotten to before we had left for lunch. So we're going to go ahead and continue. And we're going to take a look at the electron cloud model, and then we're going to contrast the two. So let's take a look at the quantum model, which, for your bell work, one of the things was, what is another name for the quantum model? It is the electron cloud model. So if you didn't get that in the video, it is here. The quantum mechanical model, which we also call the electron cloud model, is a model that tells us that electrons are not found in circular orbits, actually. So it's an improvement on the Bohr model, but rather that the electrons can be found in different areas of the atom, and we can figure that out based on probabilities. So based on probabilities, there is a greater likelihood that there are electrons close to the nucleus than farther away. And this is what the quantum mechanical model says. So it tells us that there are certain energies that electrons must have, and that the electrons are actually found around the nucleus, but we can't know exactly where they're at, so we describe it as a probability of where the electron is at, which is why it's called the electron cloud, because we don't know exactly where they're at, but we know that on average, the lowest energy ones will be closest to the nucleus, and the higher energy ones will be farther away. So there will be some similar ideas in the electron cloud model and the Bohr model that we'll be able to contrast. The thing is that to determine these energies and these probabilities requires the use of complex calculus. So the actual equations are derived from calculus. This is not the class that you need to know calculus for. So we are going to go over this theory in a very surface level manner. You're basically going to see pictures and diagrams and be like, oh, electrons can be there. You're not actually going to see the math behind why. Unfortunately. Fortunately, because it's high-level math. Unfortunately, because the math helps explain what's going on. But if you don't understand the math, it won't make sense anyway. So the way this is going to be presented to you is in a very theoretical manner instead of a mathematical manner. So we'll be looking at the electron cloud model in a little bit more depth of detail. To actually go deep into what these equations are and the math you need to know, it's actually really more into physics, and it's in a study of physics and chemistry, which isn't encountered into a third-year college class study in that major. All right, so you're just writing down what the electron cloud model is. You'll notice that here you still see the nucleus, and the electrons are not found in orbits, but the way it's described is they're found somewhere in this area of space. And the way it's supposed to be presented, this picture doesn't really show really well, but it should be darker as you get closer to the nucleus and lighter as you get further away. Meaning the greatest probability of finding electrons is closest to the nucleus, and as you get farther away from the nucleus, is less and less probability you will find an electron. So I'm giving you about a 20-second heads up that I'm moving forward. You do not need to write the diagram for this. All right. So we still have to go through some more concepts and ideas. We've looked now at the Bohr model in general, and we've looked at the electron cloud model in general. But we're actually going to have to learn more about the electron cloud model than what is presented here. And so in the electron cloud model, there is a description of how we can find the electrons in an atom, how close they are to the nucleus. And so the first thing you're going to need to write down, and so this is found in both models. is you're going to write down what each model says about energy levels. And so energy levels can be found in both models. And you're going to want to write down the bulleted point here, and then I'm going to contrast the Bohr model versus the electron cloud model. So I'll give you a little bit of time first to write. You don't have to write this Bohr model because you already wrote one earlier. So you don't have to keep writing Bohr models over and over again. As long as you wrote down one Bohr model, you don't have to write it again. So write down energy levels. In the quantum mechanical model, which is the electron cloud model, we call the energy levels of electrons the principal quantum number. And this is the way that Cambridge refers to energy levels. It is the principal quantum number. In the Cambridge curriculum, quantum numbers, there's actually a whole list of quantum numbers, and the Cambridge curriculum actually doesn't have quantum numbers in their focus of study. So in the chemistry class, in the AICE chemistry class, there's no discussion of quantum numbers beyond that of the energy level being M. But actually, the whole concept of everything you're about to see has to do with something called quantum numbers, which is a study of quantum mechanics, which is into physics, actually. But Cambridge largely leaves quantum numbers out. And so what do you need to know instead? What do you really need to know? In the Bohr model, the energy level will be depicted as the energy level is the circular orbit. That describes distance and energy. Whereas in the electron cloud model, the energy level just describes the energy of any given electron. So what energy level an electron is at will determine the energy of that electron. How the models are similar is it actually turns out to be true that the farther an electron is from the nucleus, the higher the energy it will have is. And so that's why one of the reasons we could still use the Bohr model. What differs between the two models is in the electron cloud model, we're not saying that the electrons are moving in a circular path, but rather that they could be basically darting around the nucleus. But on average, the probability of finding a low energy electron would be closer to the nucleus, and the probability of finding a high energy electron would be farther away from the nucleus, if that makes sense. So that's the difference between the two models. However, you're still going to see me use the Bohr models because it is a visual depiction of what's going on. Whereas if you're looking at just like that, it doesn't really help you with figuring out where electrons are at. And so you will still see explanations of the Bohr model, even though it is not the most accurate model, because it is the best visual depiction in terms of distance and energy of electrons. So make sure you have it down. We're going to go ahead and continue. And then we're going to get now deeper into the electron cloud model and what you have to know about the electron cloud model. The goal of, and I don't think I said this earlier, so I'm going to say it now. The goal of these 3 lessons, kind of said it, was that we need to figure out how electrons are arranged in atoms. We have to figure out how do we place electrons around the nucleus of an atom. Because we have to know where electrons are at to know how they're going to move, where they're going to move to. And so we are working on how to arrange electrons around atoms. That's where we're getting to with this. That's where this will lead up to. And so what you're going to start to see now are pieces of a puzzle. And the first piece of the puzzle is the energy level. We call this the principal quantum number, and it basically describes in the electron cloud model the amount of overall energy an electron has. So energy level 1 would be the lowest energy electron. Energy level 6 would be a much higher energy electron. We're about to move forward. Here's the next piece of the puzzle. So this is electron cloud model. So electron cloud model. And maybe the weirdest concept, maybe, that you will learn this year, but I'll try my best to describe it as well as I can. Right, everything that's in the bulleted points in your notes, you have to know what atomic orbitals are. And then the part that's on the right-hand side with the diagrams, I'm going to show you very shortly. I'm going to give you some time first, though, to write down what's here. So you have it in your notes. Okay, so I paused to give you some time to write out the bulleted points. I'm going to start talking about shortly what is exactly an orbital. So like I said, in our class for freaks, and even at the AICE level, we are not going to have to work on the complex math that describes what orbitals are and sublevels are. We only have to imagine this visually, theoretically. So I'm going to do my best to explain it. First, I'm going to go over what this is. It says an atomic orbital is, picture-wise, a region of space. Space is also volume, right? So, in which there's a high probability of finding an electron. Something really important that you can also write as inequality here. One orbital can only hold 2 electrons. It doesn't matter what type of orbital you have. If you have one orbital, it can only hold up to 2 electrons. That's what it says there. One atomic orbital holds a maximum of 2 electrons in that area of space. And so then the last bullet point says, within your energy levels, you have these things called sublevels. I haven't described what they are yet, but if you think of subatomic particle, that prefix sub is the same idea. Sub means within. You have something within your energy level that corresponds to one or more orbitals with different shapes. And then these orbitals, once again, described where an electron could be found. I'm going to give you a little bit more time, and I'm going to show you what I have these balloons out for. It's my best way of explaining what's going on. Now, I do want you to notice that what you see here, you see an x-axis, a y-axis, and a z-axis. Anybody know what that means in math? And x, y, and z, go ahead.
3D?
It's to represent three-dimensional. But it's actually some kind of complex equation to give you a three-dimensional image. That's why I said it actually writes hello calculus. But we don't need that. We just need to see, oh yes, this is shaped like a sphere, right? So the first type of orbital you have is called the s orbital. And these letters derive from the quantum numbers. All I'm going to tell you is you have to memorize them. The s orbital, whenever you see s, that means that you have a sphere-shaped orbital. And this orbital can fit how many electrons? What does it say? Go ahead. 2. So that means somewhere within this area of space, and you just like imagine this is an atom, right? Somewhere in this area of space, there are 2 electrons that are darting around. They are repelled by each other, so you can only fit 2. So far, so good? Only can fit 2 in the orbital. And so the first type of orbital you're responsible for knowing about is called the s orbital. And now that I am bringing it up, you do have to know both of these orbitals' shapes and letter designations. So I'll give you a little bit of time to write them out. The s orbital versus the p orbital. And I'm going to add a little bit more of a comparison between the two. So this was s. And the s orbital looks kind of like a ball, actually, and 2 electrons can be found in this space. There are other types of orbitals besides s that have a different amount of energy, but they can also only hold 2 electrons. So the first 2 you're going to see is s, and the second one is p. So this is the best way to show you what a p orbital looks like. And so you have to imagine, I had to do this with 2 balloons, but actually the amount of space for a p orbital and an s orbital is actually the same. So the way to imagine an s orbital versus a p orbital is if I squished the middle part of this balloon, like I just pinched it in the middle, and it didn't pop, which it would pop. But if I was able to pinch it in the middle, it would turn into this. So basically it's the s orbital that's been pinched in the middle, if that makes sense. And so the p orbital, the difference between the 2 here is the shape. And also s orbital has a spherical shape, just like a circular 3-dimensional ball. Whereas the p orbital is shaped like, they call it a dumbbell. That's the official term. But to me, it looks like 8. Like the number 8. Or like a peanut even, P for peanut. Or an infinity sign. Looks like any of those. This is the general shape of p. And so each orbital holds how many electrons?
2.
2 electrons. So s orbital holds 2 electrons, but p orbital also only holds 2 electrons. As I said, it's easy for me to use 2 balloons because it actually only also holds 2 electrons. Each orbital only holds 2 electrons. Meaning for the p orbital, it's likely that one of the electrons is on one side and one of the electrons is on the other
side.
And so one of the differences between the 2 orbitals in their shape is that in the p orbital, it's more complicated. This is more complicated than that is. There is a trend. The more complicated the shape, the higher energy. So electrons that are in p orbitals will have higher energy than electrons that are in s orbitals of space. And so that's important to know. The more complicated the shape, the higher the energy. So electrons that are found in these orbitals are higher energy than electrons that are found in these orbitals. That's something to be aware of.
Yes, you put holds 2 electrons.
Yep, they both hold 2 electrons.
Yes.
But the more complicated the shape, the higher the energy. So 2 electrons held in here would be a higher energy than 2 electrons held in here. Comparing everything else is the same, just looking at the 2 orbitals. So once again, these are pieces of the puzzle.
The more complicated the shape,
The higher the energy. So could there be more complicated shapes of orbitals than p?
yes.
There will be. For the AICE chemistry exam, which is not this class, I know that, but just some of you may take the AICE chemistry class. If you do, they only test for shapes up to S and P. They only make you memorize S and P. They don't make you memorize the more complex shapes. So that's one of the reasons I always do WWCP. I told you this before, I believe what would Cambridge do. So when I'm presenting lessons in the phrase class, I keep in mind what's needed for the AICE class. So I try not to overteach, if that makes sense. I teach what's necessary to move on. And be successful. All right, are we good to move on? Piece of puzzle. So this is another piece of puzzle for the electron cloud model. The next thing to know is something called your energy sublevels. So energy sublevels reside within energy levels. Sublevels reside means like live, but I don't want to say live because it doesn't have life. So reside, they're inside reside in energy levels and exist as a set of orbitals. This is what sublevels are. You're going to want to write that down. Also. Everything here is important. Do not write all these diagrams. You don't have to write all these diagrams, but I'm going to explain what's going on here. Do write down the title, what's in the box, and what I added. There are 4 sublevels that exist. I'll also bring that up. 4 sublevels exist. S, P, D, F. I'll pause here. So S sublevels, whenever we see a energy level has an S sublevel, it will always exist as one orbital, one sphere. However, if you have a P sublevel in your energy level, which I know sounds like nonsense coming out of my mouth right now, but like I said, pieces of a puzzle, it always comes in a set of 3 orbitals, 3CP. And D sublevels, whenever you see D mentioned in an energy level, comes in a set of 5 orbitals. And these are the 5. You do not need to memorize these shapes. But I do want to point out, is this more complicated? Do the D's look more complicated than the S or the P?
Yes.
And a key idea is that as the shapes get more complicated, the electrons would have higher energy. So the electrons have higher energy as the orbitals get more complicated. But each orbital can still only hold 2 electrons. So the other thing to note is that one orbital still only holds 2 electrons. It's just you're changing the amount of orbitals as you move through these sublevels. So S is a set of 1. I know that sounds funny. There is no set of 1, but I just like to use the same word. P comes in a set of 3, and D comes in a set of 5. Imagine if I tell you I sell you a set of something and it's 1. Set of 1. There's a pattern here, isn't there? 1, 3, 5, and there's a sublevel I put it there, but I didn't really write it in the slide. I have a reason for not writing it, and I have a reason for also bringing it up. So there's actually 4 sublevels that exist in elements that exist. So that means in nature, on planet Earth, the elements that we know fill electrons into S, fill electrons into P, fill electrons into D, and fill electrons into F sublevels. We know that to be true. The reason why, first of all, I didn't write F initially is because F is actually not tested by Cambridge. So WWCD is one of the things. But it exists, so you should be able to draw a pattern here, and we are going to talk about F in this class because it does exist, and elements naturally do exist that have F orbitals. So if S comes in a set of 1, P comes in a set of 3, and D comes in a set of 5, can you infer how many orbitals would F have? So F, and you may want to write that down, F sublevels come in a set of 7. The reason why is because it helps to understand what's going on later on. So even though Cambridge doesn't test F in their exams, understanding the maximum of how many electrons can be held in each energy level, it would be important to know all the different sublevels that possibly really exist. So F sublevels come in sets of 7. What do you think the shape of F is compared to D? F is just like a ball, right? P, you've got this, peanut thing going on. D, you've got this. What does that look like? Somebody said a windmill yesterday. Windmill, 40 clover, donut with something. Pacifier, that's how I see it. What would F look like? Be very complicated. Let's just take a look at it. Just real quick. I think for some reason when I look in F orbital, it doesn't save what I did the prior day, so I have to relook it up. You can kind of see it, right? You don't have to memorize them. But what you should recognize is whether they're more or less complicated than the other orbital. Should be coming up short. So what do we think? A daisy.
Oh, my.
Somebody said flower actually yesterday, right?
What is it complicated?
It's a daisy. The most
What is it
complicated. The most complicated is that. And so you can look them up online, what they generally look like, but you don't have to memorize them. Not that exists, but theoretically could exist, yes. We will talk about that. Theoretically, there can be more complex, but there are no elements that have filled into anything further than that. And so, well, you can at least remember that you'll never forget that, I guess.
Oh, she won't.
You'll never forget the F orbitals, because they do look like flowers. Somebody mentioned that. So anyway, piece of puzzle so far. We know in the electron cloud model, we've got the energy level. And the energy level goes 1, 2, 3, 4. The greater the number, the higher the energy. So far, so good? Then we know that there's these regions and areas of space that we could find electrons, and we call those orbitals. So these orbitals, basically, the different letters describe different what? So these different letters describe different sublevels, but they also describe different shapes, right? So if I see S, I have to think of a sphere. That's the shape that the electrons are found in that area of space. If I see P, it looks like, however you want to remember it, peanut, dumbbell. That's how it sticks for me, yeah. The official is dumbbell, but peanut. Dumbbell, they are using like from lifting weights. I don't see it, but that's what the official one is. Like lifting weights, like a dumb, that's how they said that. I think it needs an update. And then down here, you don't have to memorize these. But you should recognize that also these are single orbitals, so every single one of these orbitals holds how many electrons? Right. So what you should notice here is that this can only hold 2 electrons, this can only hold 2 electrons, this can only hold 2 electrons, this can only hold 2 electrons. So that has a big point that I need to make up before we move forward. So I spent some time yesterday. Second period was kind of entertaining while they were doing their bell work. Spent some time yesterday, but I didn't get enough time to go to the D's. But at least I can show you with the P's. This is a p orbital, right? But whenever I have a p section in my energy level, I don't have 1 orbital, I have 1, 2, and 3. It always comes in a set of 3. One that goes one direction, one that goes another direction, and one that goes a third direction. 1 x-axis, 1 y-axis, 1 z-axis. That's the way to understand it. So my question is, given that we know that 1 orbital can only fit 2 electrons, right? How many electrons could fit in the p sublevel?
6.
6. Because you've got 2 electrons here, 2 electrons here, and 2 more electrons here. So one of the things you've got to remember is when we talk about sublevel, we're talking about a set. Not just 1 p orbital, but all of them together. And that is where students get confused with terminology. Orbital, set of orbitals. Yes? There's a difference. So when we talk about sublevel, we're talking about all the orbitals in the set. So question, how many electrons then would fit in a set of d orbitals? Go ahead. 10. So it does go like that. S sublevels would hold 2 electrons, P sublevels would hold 6 electrons, and D sublevels would hold 10 electrons. And this is not because of the change in shape, but the change in the amount of orbitals. All right, so that's a piece of the puzzle. The next piece of the puzzle is so important. Make sure you write it down. If you don't know this, you will be lost in the applesauce for the rest of the lessons that we're learning this topic. So make sure you write it down. Yes.
Is this like
You can always multiply the amount of orbitals by 2. That's why one of the things I mentioned earlier, that the math you'd have to do is counting and maybe multiplying by 2. That was that comment. When we get to it. All right, the next piece of the puzzle. in quantum theory, which is the electron cloud model. This is the next piece of the puzzle. Everything here you've got to write down. In your first energy level, the one that's closest to the nucleus, there is only the S sublevel. In the second energy level, a little bit farther on average from the nucleus, higher energy, there's both the S and the P sublevels. In energy level 3, there's S, P, and D. And in energy level 4, there's S, P, D, and F, all 4 sublevels. And so this is going to bring up some ideas that I had said earlier today, but we're going to bring this back into what we learned. Write this down first, though. This is absolutely essential. You've got to know this information to be successful later on in this unit. Like once we start filling electrons into sublevels and energy levels. Yes. Yes. Hello. Thank you. Go. And this time I am actually going to encourage you, if you want to draw the Bohr model out again, this specific one right here, you should, because I'm going to show what this means in pictorial form, which I think will be helpful because it's visual, a visual aid to help understand what's going on. So I do encourage you to draw a Bohr model with 4 energy levels. We're going to start to see how this starts to piece together. So mean. I'm a terrible artist, so. Everyone has different talents. That's how it is. Okay, so I'm giving you a little bit of time so you can fill in that blank Bohr model because I'm going to add some stuff to it. If you'll recall earlier, so I'm going to use the Bohr model, even though I told you it's not the most accurate model, to give you an idea of what's going on. Remember, energy level 1 represents lowest energy. Energy level 2 is higher energy. Energy level 3 is higher energy. And energy level 4 is even higher energy. As you get farther away from the nucleus, the energy increases. That's one thing to be aware of. The next thing I want to point out is back in the day, about an hour and a half ago, we talked about the fact that you could only fit a certain amount of electrons in each space, right? You could only fit a certain amount. This is actually telling you right here exactly the amount that can be fit in each energy level. I'm going to describe it now. So go ahead, you should write this down, and then I'm just going to give you as a tool to help you visualize what's going on. Although I said pictorially it's not really accurate because remember these are areas of space that have dimensions that are really weird and complicated. So this is just to help you understand. So I'm gonna write each orbital. I'm gonna write each orbital as a circle with a letter inside. Because I am not a good artist. And I don't have the time. That letter being S, P, D, or F. Okay? Instead of writing spheres and butterflies and 4-leaf clovers and daisies, I'm not doing that. I am going to just write a circle with a letter inside. Got it? So energy level 1 has an S sublevel. How many orbitals is that? That is all energy level 1 has space to fit. Only 2 electrons can fit in the energy level that is closest or has the lowest energy to the nucleus. So the energy level 1 s orbital is the lowest energy orbital, and it is the only one in energy level 1. So far, so good? Move to energy level 2. Energy level 2, it says, has its own S, and it has P. So go ahead and let's fill that in. S is always a set of 1. P is a set of how many?
3.
Just go back to here, it's the last slide where your notes are. P is a set of 3. So let's fill that in. It doesn't have to be perfect, just P, because remember, I'm not actually writing the actual shape. I'm just telling you there's 1, 2, 3, 4 orbitals in total in the second energy level, right? 1 s and 3 p's. Does that tell me how many electrons can fit in each of these energy levels? Yeah? 8. And if you've taken physical science, you might have actually heard that before. That the first energy level holds 2, the second energy level holds 8. You might have heard this before, which we're getting to. And it is going to end up being more complicated than it was in that class. But these are pieces that connect, if you've taken those classes, into things you might have heard before. As you're building up these pieces, you'll start to hopefully make some connections. Next energy level has S, and it has P, and it has D. So in energy level 3, that third ring, S comes in a set of how many orbitals? 1, has its own S. How many P's? 1, 2, and 3. And how many D's? 1, 2, 3, 4, and 5. A whole lot more orbitals in energy level 3. Can you figure out how many electrons that would be? Well, count the orbitals, right? 1s, 3 p's, and 5 d's. 1 plus 3 plus 5 is 9, and 9 times 2 is 18. Oh. So the first energy level holds 2 electrons. The second energy level holds 8 electrons. And the third energy level holds 18. And like I said, these might be, especially the 2 and the 8, these might be numbers you're familiar with. They may or may not be, but you should write this down. This all leads up to how are we going to fill electrons around the nucleus of an atom. So write that down. The first energy level only holds 2 electrons because it only has the s orbital. That's the only type it has. The second energy level actually holds 8 electrons because it has the s orbital and it has the 3 p orbitals. It has the set of p's. And the third energy level actually has s and it has p and it has d. I don't want to do it. We'll get to f in a little bit. We're not going to neglect it. I just don't want to fill it in. If that makes sense. Too much. Because it will be 1 plus 3 plus 5 plus 7. So hopefully you have the idea here of what is going on. Yes. It will be 32. That is correct. This is a lot of patterns. There's a lot of patterns. Because it comes off of formulas. All right. I'm giving you a little bit of time, and then I believe the next slide off the top of my head from yesterday is going to be a chart. And the chart is a summary of everything we've looked at so far. So like as a one-pager. So I'm about to give you a handout. Remember, whenever you see a chart, it either means that it's a handout or it's not something you need to memorize. If it's a handout, then it is something you need to know. So we're going on to it now. This is it. This is actually everything I presented in the past hour. Everything I presented is here on this one page. I'm going to pass it out to you and I'm going to explain it, but you can see the maximum electron per energy level are here, the types of sublevels are here, and how many orbitals they are, and what energy levels you have. So I'm going to pass this out now. This goes, in your handouts. This goes in your handouts, right? Unit 2, lesson 1, so you know which lesson this belongs to. Unit 2, lesson 1. This is a summary of all the pieces of the puzzle that you're going to be putting together into a radio electron. Okay. And yes. Okay. Somebody just left and they come back. All right, so this handout you need to keep. You can use it for your homework, and you probably should, because it is a one-pager that will help you to understand what's going on. So just to describe what this tells you real quick, once again, write Unit 2, Lesson 1 at the top so you know what lesson this belongs to. See what it's saying. In the first energy level, how many types of sublevels do you have? 1. Energy level 2 has how many types? Wait, is there a pattern here too? Energy level 3 has how many types? So the energy level tells me how many types of sublevels there can be. So in energy level 1, I only have S. I want you to underline this number here and this letter here so that you can identify what that means. What does 1S mean? So later on in this class, I don't know if any of you did this in physical science, there's depending on your teacher, you might have done something like 1s2, 2s2, 2p6. If that rings a bell, that is exactly where this is leading to. That's where we're going to over the next few class periods. If you haven't heard of that before, don't stress it. I'm teaching it from scratch. So the number 1 in front here means energy level. So you should write that down. It doesn't mean amount. It means energy level. So it is a notation. It is a notation that tells me how much energy that electron has. And then what does the letter S tell me? What does that mean again? If I see S or P or D or F, what does the letter mean? Generally speaking, the shape, right? The shape of the area where the electron could be found in, and then how many orbitals it has. So S would be, it's the type of sublevel which describes the shape and amount of orbitals. So if I see the letter S as a sublevel, remember sublevel means set of orbitals itself. So if I see 1s, what's being communicated to me is energy level 1, so closest to the nucleus, and shape is S. The electrons are found in that area. Kind of make sense? So then what does, let's just look at a different one. What does 3D mean? If I saw 3D, what does that mean? Energy level 3. And the electrons here are found in the D-shaped orbitals, right? So they are found in the set of 5 D-shaped orbitals. So that's what 3D communicates. So you're going to see things like 3D5, 3D8. And I'll say what that last number means next class. But for now, you just have to know that if I see a letter and a number in this way, number then letter, and those letters are S, P, D, or F, we're talking about the energy level the electron is found in and the shape of the area that the electron is in. That is what's being described to you. So you should once again make that notation. Before we move on off this chart, could you predict n equals 5? So I told you that S, P, D, and F are all that we know really exists, actually. There are no elements that go past F. But mathematically, because these are all patterns, we can make predictions on what comes next. Once scientists discover element 121, we're not there yet. They've only got up to 118. If scientists are able to, I don't know if it's going to happen in our lifetimes, honestly. Maybe your lifetime. If scientists are able to discover element 121, it's predicted that element 121 will fall into the next orbital that actually exists. It's called G. So I'm bringing it up because it does show up, like one question shows up in the homework for you to draw the pattern, so I'm going to help you with that now. So what would n equals 5 look like? Go ahead and write this down. First of all, can you predict how many sublevels there could be? 5. We know that in reality we've only ever encountered 4. But theoretically, there can be 5. They would be called 5s, 5p, 5g, 5f, and I'm going to write 5g with a star. Why am I writing a star? Because this doesn't exist yet. It was just theoretical. It could exist though. Would G be more complicated than F? And if F was already super complicated, G's like, gotta be out of control. Out of control complicated. Well, given what we can draw a conclusion on here, can we figure out how many electrons would energy level 5 theoretically be able to hold? Do we have enough information? Well, how many orbitals is S? 1. How many orbitals is P? D is? F is? So it logically follows that G is 1, 3, 5, 7, 9. That's a pattern. So then, what would the amount of electrons that could be held in energy level 5 be? Count the orbitals. 9 plus 7. You can use a calculator. 9 plus 7 is 16. 16 plus 5 is 21. 21 plus 3 is 24. 24 plus 1 is 25. Add those numbers up. You get 25 orbitals. Every orbital holds how many electrons? So how many electrons for energy level 5? 50. Because 25 orbitals times 2. And so that's the type of question you could be asked in the homework that goes with that. So you should write it down because that way you'll be less confused when you get the homework shortly. There's definitely homework. Yes.
Lee, pardon the interruption.
Yes. Hello.
Hi, Rihanna Leon is going home.
Okay.
Thank you.
You have homework right now.
What? We're almost done. So you should be able to do the. You actually almost right at the perfect time because there's only one more thing to go over, but you could, using this method, figure out what you need to. I just need to tell you, don't do questions 13 or 14. Like just cross them out. All right. We're going to move on? Let's go through some writing all the way. So there's one more thing we need to cover before we leave, and then you're ready for the homework. And there's an alternative method to finding the maximum amount of electrons that you don't have to count all the orbitals. That's what we're going to cover last. So the last thing for the day is one of the only math things you'll see this unit. Instead of having to do this, to figure out how many electrons there could be in an energy level, there's actually a simpler method. If you know a little bit of math. A little bit. So this is it. Go ahead and write down this formula. This is the formula to figure out the maximum amount of electrons in any energy level. It is 2n squared, where n simply stands for the energy level that you're looking for the maximum amount of electrons for. So if you follow the formula 2n squared, you'll actually get all those numbers. 2, 8, 18, 32, 50, and what comes next. So you could actually be asked, and I could ask you on your next test or quiz, how many maximum electrons could you theoretically put in energy level 9? And if you have this formula, you can do it pretty quickly. And a calculator. So how many electrons could you fit in energy level 9? We know that we don't actually have any elements that exist in energy level 9, but how many, theoretically, if we ever got there, how many electrons could fit in energy level 9? Yep. So what would our idea be? We would plug in its max electron equals 2 times 9 squared. You have to follow order of operations, which means you do exponents before you do multiplication. So what is 9 times 9? You can do it in your calculator if you don't. 81. And then you would do 81 times 2, which is 160. 2. And you can do that real quickly. So this formula gives you an alternative method beyond counting orbitals that you can actually find the maximum amount of electrons in an energy level really quickly. The other method, if you don't like algebra at all, is to count up the orbitals and multiply by 2. But it would keep going. 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus 19. Like it would just keep going. So I advise for this method, actually, I think this is the easier method. but it does mean you have to memorize this formula, 2n squared. So homework time, we are about to get to the end of class. This assignment is mainly theoretical, meaning there's not really math here. And we have to, starting next class, fill electrons around the nucleus using these pieces of information. Once you receive the homework, the first thing I'd like you to do, cross out questions 13 and 14, meaning do not do them. They are the last two questions. It's on the back page and it's the whole second half of the back page. Just don't do it. You won't get extra credit for doing it. Don't do it. Haven't taught it yet. I accidentally printed them before I took it out. So take out questions 13 and 14. Everything else 1 through 12 is required to be turned in next class at the beginning of class as homework. If there's any definitions you can't describe based off your notes, you can look them up on Google. You're allowed to research your answers, but any others, you should try them yourself. I'm passing out the homework now, and then I also want to bring up, while I'm passing out your homework for the day, that if you haven't paid your science lab fee, remember that you have to do so by next week on October the 5th. So don't forget to make a note to pay your science lab fee. I do have a little paper I'll be passing out about that after I pass out the homework. I always look at him. Yes. I mean, if you want to, you can. I'm not going to give you extra credit, but that is good.
Yeah.
Here. Yeah. All right. I'm about to stop recording. Let me make sure I hit stop recording. All right. Remember, the first thing you should do is cross out 13 and 14, so you don't forget you don't need to do that, so you don't get confused. I don't want you to be confused. Next thing is just a reminder, if you haven't paid it yet, take this home. That you do need to pay the science lab fee. It's just a reminder to take home.
I give you
Just a reminder to take home. Just remember, pretty sure you did pay. We're like the first person.
what you
Out of 140.
wait, even for the triplets?
Yeah, you were literally the first person. That's why you're gonna brag about that.
Yes.
Like it went up on the system, and you paid it 10 minutes later. Like the moment it went up on AOSP, like there was no time for anybody to beat you.
I'm gonna brag.
Just a reminder to take home for the science lab.
Oh, not the non like the devil, like the demon, like the non like that. Because the non that